Welcome to e-Padasala PG program for computer science students. In this module, we will be looking at the embedded system design case study part 2. So, today we will be covering about simple digital camera. So, in this module, we will discuss about the requirements, specifications and what are all the functions we will be requiring for a digital camera, and at the end we will discuss about the design and implementation of digital camera. So, first we will look at what is a simple digital camera and what is the purpose for which this has been made, and what are all the specifications and requirements, and all those things we will first see. So, a digital camera is used for capturing the images. So, after capturing the images, in the olden days analog cameras where we will be capturing the images with films, but nowadays we will be using digital cameras. In digital camera, we will store the images in digital format, where we will not be using a film and we will be storing the images in camera. So, as we say that we are storing the images, we can store multiple images in the camera, as much as possible images which can be accommodated with the memory. We can have that much amount of images with your camera. So, the number depends on the amount of the memory as well as the bits used per image. If we store the images in the camera, as it looks like a file, image file, so it can be downloaded to PC. So, when you are going ahead with the PC, you can process anything with respect to your images. So, nowadays some of the things which are all possible are systems on chip in a digital camera is possible, as well as multiple processors as well as memories on single IC is also available. High capacity flash memory is also available. So, when you are looking at the simple descriptions used, for example, many more features with the real digital camera are the variable size images, the image deletion as well as image compression, digital stretching, zooming in and zooming out. So many things which will be possible when you are looking at the digital camera nowadays, which is not possible when you are looking at the olden days analog cameras. So, when you are looking at the digital camera in the perspective of an embedded system design, which will have a general purpose, either a general purpose processor or it will have a single purpose processor. So, it may be of a custom type processor or it may be of a standard type processor. We will have memory also, and because we wanted to download the images to PCs, so we will have a interfacing is also provided with your camera, and through which that interfaces you can download all the things which is stored in your memory of your digital camera. So, this shows about the general picture of a digital camera, where just see that we will be having a lens. So, through lens whatever be the picture it is capturing is stored on falling on to this CCD. CCD is nothing but charge coupled devices, which through the CCD it will go towards the analog to digital converter. It converts whatever be the data which is recorded through your CCD arrays, and it is pre-processed through this CCD preprocessor, and it comes to your microcontroller. So, in an embedded system, either a microprocessor or a microcontroller is used inside, so which takes care about further processing inside it. So, the CCD pre-processing is done through this particular person, as well as we will be doing something like a pixel sometimes we will have a pixel coprocessor is also there. So, along with these persons, he will do all kind of processing inside it. That means it converts the digital informations. It has been compressed using a JPEG codec, and in a memory through DMA it can be a DMA as well as a memory controller is also there. With the help of these persons, the compressed images can be stored inside the memory of this particular digital camera. As we know that it can be sent to, when you are taking a picture, we wanted to see that in the screen while you are taking it. So, that also can be possible while you are, it comes through this particular channel, and digital to analog it is again converted, and it will be shown in the display screen, that means LCD panel. So, when you are looking at what will be the data which we have stored, that means with the camera we have stored so many images, this can be sent to your PC through this UART. That means the serial communication interface is available with your digital camera. So, through which the what will be the data which is stored in this particular camera is sent to PC, so that you can process with your PC. You can download all the images which is stored inside your digital camera, where when you are looking at the images, it can be given in a different sizes also on the display screen through the different processing. So, remember that there is a processor inside it. It takes care about all the process which has been done with inside your digital camera. So, usually the camera is for taking photo. So, it is a single function and it is tightly constrained. So, what are all the constraints we will say is, with the digital camera it is of low cost, low power, and it should be a very compact size, and it should be very fast. So, these are the constraints always people will look at, and it is only to a smaller extent it is very reactive and to the real time. So, when you are looking at the digital camera in a designer's perspective, I will say that there are two things. One is processing the images and storing in memory, another one is uploading the images to PC. So, when you are looking at processing the images and storing in memory is, when the shutter is pressed, that means while you are clicking to take a photograph, so that the shutter is pressed. So, by the time the image is captured. So, the captured image is converted into digital form by the charge coupled devices. So, this this converted digital form is compressed and archived in internal memory. When you wanted to upload these images to PC, then the digital camera is attached to PC. The special software commands of the camera to transmit the archived images serially to PC. So, when you are, as I told you, with your digital camera, what will be the scene which is exposed to it, that means if I am looking at the physical, the scene or a picture, some object you wanted to capture it, which will be placed over here. So, the in front of the CCD, that means through the electromechanical shutter, the electronic circuitry which captures the images and which will be placed onto this particular CCD array. So, here we will say that the electromechanical shutter is activated to expose the cells to the light for a brief moment. So, now the electronic circuitry which is commanded and discharges the cells activates the electromechanical shutter and then reads the 8-bit charge value of each cell. Then these values are clocked out of the CCD by external logic through a standard parallel bus interface. So, now all these things are given to your charge coupled devices, so that you just see that the special sensor, what way the image is captured, that is very important, where we will be looking at your charge coupled device. So, the special sensor which captures the image. So, the CCD is we will be having something like this particular part is nothing but a light sensitive silicon solid state device composed of many cells. As you see that the whole thing is having a different cells, each cell I can refer it to a particular pixel. So, each is exposed to the image. So, now when it is exposed to light, each cell becomes electrically charged. So, now these charge can then be converted into 8-bit value, where the 0 represents to no exposure, while 255 represents a very high white color that means very high exposure towards the light. So, here these things are when the image is placed placed and the image is captured, then this image is converted into electrical signals through which this goes through the electric circuitry, it goes outside. So, some of the columns here which is covered with a black strip of paint which is for correction. otherwise I will call it as zero bias adjustment for the cells. So, now we will see that the charge coupled device is the interface between the outside world and to the inside, so that the image is captured, captured image is converted into electrical signals which is sent inside. Now, the data which is maybe, for example, I will say that this is the data which is available in your charge coupled device. Now, when you are covering the data, these are the places where we made some black strip is placed over there. Just look at over here, this black strip is placed over here for zero correction, zero bias correction. So, when you are capturing the image, I will get this kind of data. So, these are the places where I will say that the object is exposed, so I will get a value. But remember, the black color strip is placed where it has to show only 0, but it is giving you a value of this particular one. So, it shows that each and every row is having one data which says that this much amount it is giving you the excess value. So, instead of giving a 0, it gives you 12 and 14. That means, we need to say that 30 on an average 13 is increased in this this particular row. Because of that, I will find out what is the average. So, 13 is there. I will, for zero bias adjustment, I will subtract 13 from the whole row, so that it has been zero bias is done, so that it is corrected to this particular one. So, now you just see that if I am getting a 0 0, then 0 is subtracted. If I am getting 5 5, I have subtracted minus 5 with the whole row. If I am having 7 and 7, minus 7. If it is 2 0, minus 1 is subtracted from this particular whole row. So, that way, so the captured image is corrected, so that we will be getting the getting a result which does the zero bias adjustment. Now, we got the data, but we can't store it as it is, because it will be, because the device is having a limited memory. With that memory, we wanted to store more number of images, then it is not possible, we can't store it as it is. So, we need to compress the images based on, then only we need to store these images. But remember that while during the compression also we should not lose more information about that particular image. That also has to be considered while you are compressing and storing the image inside your digital camera. So, if this is the case, now the JPEG is the format with which the images are stored. So, in this JPEG is a popular standard image format for representing the digital images in a compressed form, and it provides a number of different modes of operations, and this particular mode provide a higher compression ratio using DCT. So, using discrete cosine transformation, whatever be the data we have captured is compressed. So, remember in the JPEG when you are converting the images into compressed mode, there are 3 steps we have followed, so that the maximum compression is done with very less loss with respect to image also. So, one is DCT, next is quantization, another one is Huffman encoding. So, by following these 3 steps, each block will be compressed and we will be storing it with a lesser values. Lesser size is required to store this particular images. So, when you are as we know that DCT is nothing but discrete cosine transformation which is applied to the image. So, after processing it, it has to, again we have to apply the inverse DCT, so that it reverses to the normal size. So, when you are normal world, that means time domain. So, when you are looking at these are the images, if we got it after DCT, then this values are of higher values. So, what we thought is we wanted to store each and every, see 11150 is there. For storing this particular value, definitely 8-bit is not sufficient. So, what we thought is the whole thing, each and every pixel has to be quantized in such a way that maybe 8-bit is more than sufficient to store all the values. So, the quantization is done and we will be getting a value like this. It is comparable to this particular value, but it requires only 8 bits to store each and every values. So, that way the quantization performed, so that the number of bits required to store the whole image is less. But remember, after quantization also we can approach, we can adopt some of the techniques, so that still the image is getting compressed. So, for that people are going towards the Huffman encoding step, where when you are looking at Huffman, before Huffman, the whole data, maybe it looks like a matrix, rows and columns. This has been made it into the zigzag pattern like this. Each and every thing, when the line, when it crosses, will take that particular pixel. So, that way the whole image is made it into a serialized format. That means we will say that the values are converted into single list using zigzag pattern. So, instead of having a two-dimensional data, now the whole image is converted into single list using this particular zigzag pattern. So, wherever the line crosses, that particular pixel is taken. So, this is the way the whole image is traced, so that the whole image is given as a single list. Then after that, this single list pattern is sent through a Huffman encoding scheme, through which it has been reduced to a appreciable level. That means Huffman encoding is a very famous encoding with respect to communication techniques, where we will be using that particular technique for storing the images as well as reducing the size also. Here you just see that these are the pixel values with which we have given along with the frequencies. So, instead of storing all the values in a fixed length, people are thinking about the variable length with respect to Huffman encoding. So, with that we made it, if it is -1 is appearing for 15 times, then we will say that that will be the maximum number of frequencies which is occurring in this particular list. So, this value has to be represented with a very less number of bits. So, just see that -1 is represented with only 2 bits. When you are looking at 144, where this is appearing only one time. So, this has been coded into the maximum number of bits, maybe 6 number of bits. So, that may be the maximum number of bits. So, that way when you are looking at the frequencies, if the frequency is less, maybe that will be represented with more number of bits. If the frequency is high, it will be represented with minimum number of bits. So, if that is the case, then we will be in a position to represent these values, or we will convert the whole image into this variable bit format, so that the number of bits required to store this, the whole file, will become reduced to a greater level. So, Huffman encoding also helps to reduce the size of the image to be stored. So, we just have it something like more very big image, but it has been compressed using your JPEG format, and you will get a very less, so that it will be stored in your memory of your digital camera. So, when we store the images to your memory, then this has to be connected to, when you wanted, that has to be transferred to your PC, then there should be an interface between the PC and your camera. So, there we will be having a serial port using supported with UART, is available with your embedded systems. So, we have used that particular port through which your system serial port is TCP, your RS-232 port is connected along with your line driver, so that this will be transmitting the data towards your PC and you can store it. So, while transmitting, we have to reset the pointers, the image size variables, as well as the global memory pointer accordingly. So, when you are, so we have discussed about the whole process concepts with which how your digital camera works. All those things we have discussed in the previous slides. Now, we will see that what are all the requirements, and based on that how we made the specification for the digital camera. So, when you are looking at the system requirements, we will have two kinds, one is non-functional requirement, another one is functional requirement. When you are looking at non-functional requirement, which basically tells you about the design metrics. When you are looking at the functional requirements, which tells you about the system behavior. So, we will say that if I am looking at the system behavior, we will say that how much resolution it can capture, as well as how much precision it can give you the details. So, all these, the system behavior has been defined with the functional. The non-functional tells you about the design metrics, such as your power, dissipation, and all those things. So, when you are, but usually when you are looking at the specifications provided by the marketing department, they will say that what will be the cost, what will be the battery life is required, as well as how many resolutions can be captured, and how much you can load it to your PC. So, all those things they will give it as the specifications to the people who will manufacture the digital cameras. So, non-functional requirements where we will say that, as I told you, the performance, size, power and energy. So, these are the things we will be concentrating on your non-functional requirements. So, when you are looking at constrained metrics, values must be below certain threshold, as well as the optimization metrics are improved as much as possible to improve the product. So, you can have metric both constrained as well as optimization. So, when you are looking at the performance, it should process the image as fast as possible to be useful, as 1 second is reasonable constraint. So, size, we can say that the camera should be reasonably sized, and will have a minimum number of gates, so that we can have a lesser size as well as the cheap rate is also less. The power, always it should operate with a lower power, so that we have to maintain the temperature below certain threshold. So, remember, there is no cooling fan, which is cooling fan cannot be attached with this digital camera. So, we need to operate always with a very less temperature. So, when you are looking at energy, we need to reduce the energy consumption. So, when you are looking at the functional specification, as I told you, the camera should have the different functions, it has to satisfy all those things. So, here as we discussed, the CCD through whatever be the image we wanted to capture, which has been captured by your charge coupled devices, and this will be given to a zero bias adjust. From there, after adjustment, it will go to discrete cosine transformation. After that, it will go to quantization. After that, it will come to the memory, where you will be storing it. So, while you are storing it, you will be storing it as a variable length or a fixed length. Variable length means we will be looking at the Huffman code, so through which it will be compressed and it will be stored. So, if you wanted to you want more 8 into 8 cross blocks, then it goes in a loop. So, if I wanted to if I am thinking that this is more than sufficient, then I wanted to store it. If I wanted to transmit serially to my system, then it will be sent through this. So, this has been sent through, supported with UART, and it will be passed out so that the system reads, that means the PC reads the things. This is the functional architecture or functional specification with respect to your digital camera. So, this is the refined functional specification, which tells you about what are all the codes which will be used to provide all those things. So, this is an image which is having a 0, 1, 0, 1, 1, 0, that means the pixel values. So, this has been sent to your CCD processing module. Then from there, pre-processing CCD pre-processing module, it will go. Then it will go to control, where it does all your compression. So, all your compression is done with your codec and all those things. So, you just see that these will provide you the digital images which has been sent to through your UART, it has been sent to your output file to your PC. So, this is actually tells you about the functional specification with respect to your system. So, any programs for your digital camera can be written either with embedded C or C code, whichever has to be supported by the controller which is available with your microcontroller or your microprocessor placed inside your digital camera. So, when you are looking at this code, so you just see that we will be right. This is a sample code. When you are looking at the real, CCD, which simulates. This is for simulation of the CCD. So, it tells you that rows and columns. If it is 6 rows and 6 columns, then each and every pixel will be simulated, so that it gives you just like it simulates just like a real CCD. So, when you are looking at CCD pre-processing, which is nothing but your zero adjust, so that has been done, finding out the column as well as number of columns and rows where you will be having a zero bias is found, then that will be subtracted, and the 2 pixels with zero values, it is added whatever be the values which we will be getting it, which is divided by 2 averaged, and that will be subtracted from, that will be the bias which is subtracted with your real value. That is nothing but your CCD pre-processing, which is zero adjustment. So, that is the way you will be writing all your code either with C or C++ or embedded C, which will be supported by your processor placed inside your camera. So, now when you are looking at the design, we will be looking at either we will have a single processor or we will be having a general purpose processor, or we will have a multi-processor also inside it. So, but along with the processor we will have a memory, buses and many controllers. So, when you are looking at the functionality to the architecture, multiple functions can be done with one processor, or one function on one or more processors, or the low end general purpose processor which is connected to the flash memory. So, all functionalities are mapped to the software running on the processor, and it satisfies the power, size, time to market and constraints. So, if the timing constraint is not satisfied, then the limitations could be of single purpose processor for time critical functions. So, if you need to improve the time, then we need to concentrate on a good processor or multiple processors to do different works. So, that is the way people have enhanced the problems, rectified the problems or enhanced the system performance, and maybe we can rewrite the functional specification so that we can compensate these problems. So, when you are implementing it, I will say that the architecture, a particular architecture and mapping can be used. The solution space is set for all implementations. So, when you are looking at implementation, people did with only the microcontroller, only a single microcontroller, or they have done it with this microcontroller and charge coupled array preprocessor, the microcontroller, charge coupled array processor, fixed point DCT together, or the microcontroller and the CCD-PP and DCT. So, the different combinations they have tried, they have implemented, and they found that they have compared the process or the performance of these systems. Based on that, they have decided what can be chosen for which kind of applications, what can be chosen for which kind of applications. So, now when you are looking at 8051 microcontroller, people will say that it is cost is very less, but it is 12 megahertz, 12 cycles is taken, and the CCD arrays has been taken. So, the budget is very less, but it has a over budget for adding compute intensive DCT and Huffman coding will be over budget. These will not have a high budget, but this will cover a over budget, but the time taken to do it with only microcontroller will make it the work will be done with slightly slow. So, when your second implementation, when you are looking at your CCPP, DPP, there microcontroller along with CCDPP. So, when you are looking at it, it improves the performance, cost is slightly high and easy to implement, it is simpler data path and few states in the controller. So, when you are looking at the third implementation, where the microcontroller CCDPP as well as the fixed point DCT is also along with that we have done it, because we make a fixed point processor for doing this DCT. It can be done very fast. It is a floating point operations per pixel transformations. So, the DCT requires 260 floating point operations per pixel transformations. So, remember that per pixel it requires this much operation. So, that way when you are looking at 64 cross 64 pixels, then 4096 operations per image DCT uses. So, if that is the case, if I am looking at separate DCT board, then this can be handled very easily and the time taken is very less. So, when you are looking at the microcontroller CCDPP and fixed point DCT, when you are looking at, the time taken is very less, but the power consumption is also less, but the total chip area is 90,000 gates, and battery life is also very, battery life is 6 times longer, and only thing is it is more, because we have adopted many things, it is expensive. So, and the time size also will be slightly higher side. So, when you are comparing these kind of things, either we will have microcontroller alone or will have a different processors for each process, and it is combined together to improve the time. So, that way if I am looking at which improves the battery life as well as time taken is very less, but the power is, I mean, the significant increase over previous implementation has been achieved. Performance is very good and the energy consumption is also reduced. So, when you are, but the major drawback is more expensive and it may miss time to market window also. So, when we made it, all these things combined together, they have done all the implementations and they have compared it. You just look at over there, it gives you a good results where with only microcontroller kind of system which takes more time. When you are looking at the different processes as well as the each and every process is done with one process and everything is attached together, so that it takes only 0.099 as the time seconds. So, I will say that only microcontroller, if I am using it, it is too slow. But when you are looking at the co-processors, these things has been implemented with so many co-processors, which gives you a better, but still too slow. I mean, when you are looking at it is better, but I mean, when you are looking at the last one is nothing but additional coprocessor for compression, which makes fast enough but expensive and hard to design. So, the implementation 4 is along with this this kind of information. It is very fast but expensive. But when you are looking at it is too slow, but it is not complicated also. If you are looking at only a very low end applications, then you can go ahead with only microcontroller. If you wanted to have a real time application where you are targeting only the time is very you can't spend time for that, then you go ahead with microcontroller along with so many coprocessor, so that it is very fast and you will receive whatever be the response you expect from this particular digital cameras. So, in this lecture we discussed the one case study, that is digital camera, and we have discussed about in detail what is the requirements as well as specifications for digital camera, and we discussed the functions of each and every part inside your digital camera and how it has been designed, and we have how it can be implemented. That has been discussed, and with respect to time, which kind of model can be preferred, that also we have discussed. I mean, we made so many analysis. With that we have found that based on the timing requirement, we can select the co-processors also. So, this is the reference, we can use it for your digital camera design. Thank you.